Well, good afternoon. This is 12:26 in the afternoon. We're supposed to be in Cal 3 right now. However, I'm the only one in the room. A student has been in here, but she just walked out before I got back. I've been having some problems with projection, computer to projection communications, and I think I've sort of got it worked out with one possible still thing to check, but we're going to get started on class today. I did have a few announcements, but by the time I make them, I think some of them will be over with, but I think I'll go on and make them now rather than wait any longer. Let me see if I can find them here. Okay, here we go. I've been announcing for well more than a week about Cougar Connection Week. Today, and you can't go to it because it'll be during class, and it'll be over with by the time you hear this anyway, so I'll just leave that off. If you're on the Birmingham campus this afternoon at 3 o'clock, they have what they call Serve Day. I don't know what that's involved with, but you'll have to check it out. Birmingham, I'm sure it's the West Campus, Serve Day after 3 o'clock. Now tomorrow, since we're not going to meet tomorrow, so I won't be able to tell you that, let me tell you what's happening, and there are two parts to this, actually more than two parts, but on the Birmingham campus, now everything's on Birmingham tomorrow, the student organization induction ceremonies are being held tomorrow in the A.G. Gaston Auditorium on the Birmingham East Campus, and that's at 1 o'clock in the afternoon. Okay, 1 o'clock in the afternoon, and I'll give you a little more detail about that later. Later in the evening, at 4 to 6, there is a pool party. The location is the Arthur Shores Fine Arts Building, which is also the gymnasium, which is also the weight room, which is also the pool, okay? You just have to go a little bit deeper into the building to get to the pool. Fantastic, very nice indoor pool facility there, and the pool party will be there this afternoon tomorrow afternoon from 4 to 6. Okay, now a little bit more about the induction ceremony. They sent this announcement yesterday, yesterday. Come witness the installation of your Student Government Association officers, the Lawson State ambassadors, as well as the induction of members into Phi Theta Kappa Honor Society and Kappa Beta Delta Honor Society. Okay? This will be at 1 o'clock tomorrow in the A.G. Gaston Auditorium. Okay? This is things coming up with Cougar Connection Week. The Student Government Association, Ambassador, Honor Societies, that kind of induction tomorrow at 1 o'clock on the Birmingham East Campus, A.G. Gaston Auditorium. The guest speaker is Mr. Galvin Billups. He's the Executive Director of the Mayor's Office Division of Youth Services, the City of Birmingham. And the program will be tomorrow, the 20th, 1 o'clock, A.G. Gaston Auditorium. Now, that almost wraps up Cougar Connection Week. The only thing is, one thing's going to spill over into next week. I think they're going to have a blood drive next week. They couldn't schedule it this week. They tried, but they couldn't get it here. Yeah. All right. How close are you to graduation?
4 semesters.
I'm sorry?
4 semesters.
Oh, really? Okay. Well, I don't know about the others in the room, in the class. They're not in the room now, but in the class. Light here. But in case any of the rest of you guys are close to graduation, here is first a warning and then a recommendation. If you're graduating this term, fall term, now they sent this Monday, I've been announcing it all week, please note that the deadline to apply for fall term graduation, that's this term, is tomorrow, okay, September the 20th. So please, if you are graduating this term and you haven't applied to graduate, please get the application in tomorrow. Now, there's now 3 steps to the process. First of these is what they call a degree audit. And I think what that means, I'm not absolutely certain, but I believe what it means is you pull up your degree plan, the most current version of your degree plan, of the degree that you're currently listed under, and it shows everything that you've taken, everything that you're currently taking, and also then it'll show anything that you have left to take. Then go take that with you to see your advisor, and once you've seen your advisor, then you apply to graduate, and it's all done online now. There's no more paper copy. So anyway, they've got some flyers posted in some places. I haven't seen as many as I have on some of the others, but there are some posted. Take a look at those. Go to records office or registrar's office and check out anything that you have questions about. Now, here's two opportunities. Are you on Birmingham and Bessemer, or just Bessemer? Both? Okay. You may really be interested in one or both of these. The Office of Student Services is seeking students who are interested in becoming note takers. Now, here's just a little bit of background from my perspective. About 2 or 3 years ago, I had a student in my physical science class who had a pretty severe case of cerebral palsy. So he was in a wheelchair, had limited mobility. He could not use his hands well enough to take notes. So our Office of Disability Services provided note takers for him. So that's what they're looking for. And it sounds like it's on the Birmingham campus, so I'm not certain. It's Ms. Janine Jones who's put this out there. She's Student Services Specialist on the Birmingham campus. And I've got her email address, jjones@lawsonstate.edu, and I've got a phone number if you want to give her a call. But it looks like she needs some note takers for fall. We may need them on this campus too. If you want to check on this campus, Dr. Renee Herndon is Ms. Jones' boss, actually, so you can check with her. She'll know all about it. And they do pay you. It's not a gratis thing, though it's a really nice thing to do, but they also pay you, so that's nice too. Now, in addition to that, the Space Center is looking to hire, okay, they pay you, peer tutors in the areas of math. You'll be superior in that. English, biology, computer science, and Spanish, okay? The interested students may contact Ms. Leslie Harper. Again, she's student persistent counselor on the Birmingham campus, I think mostly. Her email address is lharper@lawsonstate.edu, and I have a phone number as well. But we have a Space Center on this campus too. They do provide tutoring, so either campus you should be able to, if that's something you have interest in. And frankly, that's where I learned math the most, was tutoring others. I could pass tests nicely, easily, okay, just studying on my own, but boy, by the time I had to explain it to somebody else, I knew it, okay? So it's really a positive thing, and they pay you to do it. So, I mean, a win-win-win situation. You're helping somebody else, you're helping yourself, and you're getting paid to boot. That's not bad. All right, any questions on anything we've done up till now? All right. Well, I had the projector on, and when you weren't in here, I turned it off again and disabled the bulb, but I forgot to turn it back on. I was worried when I first came back from the going down the hall to return the other cord that I had. When I came in, the projection was very pink. I thought, oh no, I just gave away a good cord, and this one's not doing well. But then I tightened it in the back, and it came on better. So here it comes. Now this is example 1. We've already done example 1 and 2, and we're on page 838 in chapter 12, vector valued functions, 12.3, velocity and acceleration. And example 3 is not on the slide set, but it is, let me wait just a minute, let me get my pen activated again. It is at larsoncalculus.com for an interactive version of this type of an example. So if it's not exactly, it's one very similar. It says, sketch the path of an object moving along the space curve C, and here's the space curve, R of t is equal to ti plus t cubed j plus 3tk. Okay? And this is for any t's greater than or equal to 0. Okay, moving along that curve. Now it says sketch the path. I don't do a great job of sketching. Do you have either an ebook or a book? You have it. Okay, do you see the sketch there? It's figure 1215. Okay. Just pretend I sketched that. Okay. All right. It's not an easy thing to do, but it's not impossible either. They give a reasonable perspective there I never would have thought of doing, with the x coming out this way and y back that way and z up. But you see when you can just plug in some values. Of course, at time t equals 0, that would be at the origin, 0, 0, 0, okay, from this equation here. At t equal 1, that would be I plus j plus 3k. So you haven't gone much on I and j, but you've gone up 3 on k. When t is equal to 2, you're 2i plus 8j plus 6k. So now you moved a little bit on the I, huge amount on the j, and a little bit on the k, a little bit more on the k. Then when you go to t equal 3, you'd be 3i plus 27j plus 9k. So you're really moving on the j, on the y-axis. So that's why they pointed the y-axis where they did, so it follows out that way. So anyway, there's your the path that you're taking on that space curve C. Okay. It says find the velocity and acceleration vectors when t is equal to 1. So how are you going to find the velocity vector? It's the first derivative of the displacement vector. So that will be what? I plus 3t squared j. What's that? Plus 3k. Okay? Okay. All right. Now, while we're doing this, let's just carry it one more step and do our acceleration vector, because we're going to need it anyway. So always calculate the vectors. Yes, I hope I don't forget them. Okay. Always calculate the vectors from the original, but then plug in at the end. But let's go on and do acceleration vector, which is the first derivative of the velocity vector, which is also the second derivative of your displacement vector. That's supposed to be an R there. And what will that be? Say 6tj. Done. That's it. The acceleration is strictly in the j direction. And boy, is it moving in the j direction. Okay? Now, let's calculate those at t equal 1. So what is the velocity vector at t equal 1? I plus 3j plus 3k. Okay? There it is. Okay? Slightly positive in the I direction, much more rapidly positive in the j and k direction, the y and z directions. How about a of 1? Acceleration at t equal 1. It's just 6j. Perfect. Okay? And so it's all of its magnitude is in the y direction, in the j direction. The acceleration is, and the velocity, though, is sort of evenly split between y and z, j and k directions, with a little bit, a small component in the I direction. All right. And they show those in the illustration too. You find first the location. Now, we didn't actually find that location, but you could. When t is equal to 1, your r of 1 would be what? I plus j plus 3k. Actually, we had said that before. I just didn't do it as part of the problem. So you've just moved a little bit in the I direction, a little bit in the J direction, and pretty sharply in the K direction. Okay. Now, as I look at that picture, I'm sure there's some reason why they did y is equal to x cubed. That is the projection of this curve on the xy plane, but I can't see. Oh, wait. Yeah.
Because it's T pi is just x, and it's T cubed.
Yeah, they say it's on a cubic cylinder. And I can see part of that, but not really, because if that had been 3K, yes, that would have been absolutely true, but it's 3TK, which means it has a T dependence going up as well, going up the z-axis. So I don't quite see how they can call that a cylinder. Maybe they can, okay, but it's, I don't know. I'd have to do some thinking on that, and I'm too tired to think. Okay, so let's move on. We did everything they asked for, okay? Now, before we get to the next, they didn't do example 4 either, so let's do this one. And by the way, when you go to larsoncalculus.com, I'm sure he's going to give a lot more interaction than probably what I just did, or at least that much. So you might want to give that a look. Example 4 is not at that, but let's see. An object starts. Let's go and erase what we got. It's okay? Okay. All right. Example 4. An object starts from rest at the point of 1, 2, 0. Okay, if I could draw, I'd draw it for you, but I don't. You can look down at figure 1216. I think that's going to be it. Okay, starts from rest at 1, 2, 0 and moves with an acceleration. So this time they start with the acceleration vector, and this is j. Get out of there. Okay, this is equal to j plus 2k. That's the acceleration vector from that point there. It starts from rest. Now, what does it mean from rest? Not moving, so its initial velocity is 0. So we can say VI, that's what I call initial velocity, is the 0 vector, not moving at all. Okay? So whenever you see from rest, that means this object starts from rest at the point, so this is the initial point, 1, 2, 0, and moves with an acceleration of j plus 2k, where the magnitude of acceleration vector is measured in feet per second, or feet per second squared is easier to write. Find the location of the object after 2 seconds. Okay? Now, how would you proceed? Now, I'm going to do one more thing. I hope you'll count it as legal, okay? When they say it starts at this place, that means the RI, the initial displacement vector, is I plus 2j, which is not quite the same as the other, 0k. That is his initial position, okay? Initial position, I plus 2j, okay? Now, when I say initial, and we're talking about time, and I think you pretty much have to assume the initial position is also your v at time t equals 0. Now that's a vector there, not a scalar 0, it's a vector. So that would be the same here. R at time t equals 0 is I plus 2j. Okay. that done, let's see where we go from here. Find the location of the object after 2 seconds. Well, what we have here, and I don't know if we've run into it in this text or not. I've taught from so many different calculus texts, and this is the first time I've taught this course from this. I've taught the Cal 1 and Cal 2 from it before, but not Cal 3. So I just can't remember if we've talked about initial value problems. Are you familiar with that term? Okay, what that is basically what we've got here. We have a situation here with initial condition of the velocity and initial condition of the displacement. That's why I wrote them in this form. I put i's here, which meant initial, but I wanted to emphasize this is when t is equal to 0. That's your initial. Now, that doesn't always have to be the case. T could start anywhere you wanted it to, and this problem doesn't specify it, but I think based on what they're saying, you have to make that assumption. Okay? So, how do we get, and what are they asking for? Find the location of the object after 2 seconds. Well, location is your r vector. So we need to get from the a vector to the r vector. How do we do? Any ideas? Antiderivative. You're absolutely right. Since your acceleration function, vector, is d by dv of t by dt, right? First derivative of the velocity vector, remember? Therefore, we can, and that is j plus 2k. I'm doing a few tricks here. Then you can say d of v t is equal to j plus 2k dt. What I did was, looks like I multiplied both sides by dt, but really what I did was write it in differential form. That's what mathematicians like to say anyway. Okay, so that's what we're, and like you said, we integrate both sides of this, and that gives us a velocity vector. So the v of t, because the integral of the derivative is, by fundamental theorem of calculus, just the function, which is v of t. Now, what would the antiderivative of j plus 2k be? Second. Tj, Thomas Jefferson, okay, plus 2tk. All right, very good. And you might have a plus c in there, right? Because that was an indefinite integral, right? How do you evaluate what the c is? Well, you know when t is equal to 0, your initial value is equal to 0, right? So let's plug a t equals 0 in there, and you get 0, so c must be 0 also. So this c is equal to 0. No sweat there. Oh, Terrell decided to show up today. That's so good to see. Okay. Actually, we got off to a late start because I had a minor disaster this morning. My little knob here on the chair caught my cord that links the projector to the computer on it, and I went to do something, pulled the computer onto the floor, crashed, broke a little bit of plastic, but then I couldn't get the computer to talk with the projector anymore. So we tried, and this person who was in my class, and her dad worked on computers, she was convinced my computer was busted. And I said, well, I had another class, the Cal 2 class happening, and I had to check out a computer from the library, but it didn't have Screencast-O-Matic on it, or not the version I used. And so, but it would talk with the thing, but actually what we did, after many goings around, I finally got her to take my computer and the cord down to another room that was empty and play with it there. No, I left the cord here. There was a cord in the other room. As soon as you plugged it into the other room, it worked. So then we thought it was either the box here or the cord. It turned out being the cord. So I've robbed a couple of cords. This is my second and third ones that I've taken. I'm going to see what works and what don't, and then return them to the places that I got them. I already returned one, but that's why everything's been slow today. So anyway, we're doing example 4 on page 839, section 12.3, velocity and acceleration, in chapter 12, vector valued functions. Okay, and we just determined, say that again? Do we have what?
Wouldn't it have an I? The derivative of I is 0.
Yeah, and if you had an I, the coefficient would be 0, yeah.
Yeah, but I'm saying like on the acceleration it doesn't have an I, so wouldn't it have one for the velocity? So we go back to the displacement.
Okay, in other words, is this a constant? Just say C1, I. Yeah, it could be a constant. You're absolutely right. It could be. Okay? Now let's look at it when V is equal to 0. Okay? And that's probably the better way. That's where we should put our constant in. Probably right there. And then when we put t equals 0, this C1 that I called it is also going to have to be 0. Because the velocity vector at time t equals 0 is 0. So if you put it there, the constant there, it's also 0 when you plug that in. Because this, when t is equal to 0, that's got to be 0. And if C1 was anything other than 0, it would be C1i. So C1 must be 0 too. So I'll put it down there. All right. Well, now we got our velocity vector. What is the velocity vector? The velocity vector, and that should have a vector symbol over it, as a function of time, is this tj plus 2tk, okay? And what I meant to put, I was all set up to, and I got thinking about something else. Let me do it backwards here. V of t is also dr of t dt, right? So just like we did before, if we move the dt over here and integrate both sides, now we get our r of t is equal to, and just like you said before, and this is a good way to do it, want to call it C2i, and integrate the tj, antiderivative of t, antiderivative of t. 1/2 t squared, so that'd be t squared over 2j, and plus t squared k. Okay? Okay. Now, when t is equal to 0, your r is I plus 2j. So r of 0 is equal to I plus 2j. Okay? Now, and I guess I still need a plus c out here, okay? That's going to be a vector c, by the way, too. It's still necessary, okay? Other one was 0. This one we are going to need to have. Because when r is equal to 0, obviously your C2 has got to be 1, right? Because When you plug in a 0 here, you need that to be a 1. So C2 is going to be 1. So that will be the same as that 1. Over here, t squared over 2 has got to be 2. Oh, I'm sorry. 0 squared over 2, which would be 0j. So this C vector here must have, and you could either have done the C2 with the I or have it out here, this must have a component of 2j. It has to, because when t is equal to 0, this component is 0. And the k part, there wasn't a k part to begin with, so you're perfectly all right. So what your R vector is, R of t, is going to have to be I, no, I'm sorry. Yeah, that's right. I plus, and then you have to have both of these j components in it, so t squared over 2 plus 2j plus t squared k. Okay? That's going to be your R of t. And to whoa. Okay, I was afraid I was dragging it again. Okay, to check it, put it as t equals 0. That's still I. This is still 2j. Oh, right. Let me do it like that so it's more obvious. Whoa! No, okay. I don't know why that disappeared. Okay? When t is equal to 0, you get the 2j, and when t is equal to 0, you get no k. And that's exactly what you had up here. So this must be the, and you take the derivatives and you get back here, so everything pans out, just like it should. So there's your displacement vector at any time, but your initial conditions, oh wait, that's not what I asked for, is it? Find the location of the object after t equal 2 seconds. So this is your R of t. Now we plug into that R of 2, and what do we get? Well, you still got an I plus, and when you put 2 in for j, up 2 in for t, what do you get? 4 divided by 2 is 2 plus 2 is 4j, and then 2 squared is plus 4k. All right, so there's your position at t equal 2. And if you want to write that back as a point, that would be 1, 4, 4. There's where you would be at 2 seconds. Okay? And they show it first as a position vector, and they also on the graph show it at the point 1, 4, 4. Now, what I find surprising, no, I don't, after all, okay, because you have a constant acceleration, because there's no t dependence on that, you have a linear velocity, and since you have a linear velocity and a fixed endpoint, you have a straight line. So, yeah. So this is going in a straight line. I almost found it surprising because you had t squareds in there, but no, that is a linear situation. All right. Any questions on that? I know it was sort of messy here, but that's what you have to do. You have to introduce constant vectors in every time you do your integration. And some of these you could introduce in the I component here, but usually it's better just leave it as it is. But in that first one, this is 0 at t equals 0. That's what it's supposed to be, so that C vector that you added had to be 0 as well. However, this one, when you integrated that, and you could have introduced your I in there, or you could have waited and introduced it in the C at the end. It really doesn't matter, but that is a vector at the end. And those are constant components, though. So that's why this constant component could have gone down there or here. It doesn't matter which. But it are constant components. And then when you plug in your t equals 0, you're supposed to still get the I plus 2t. And so you'd have to have a 2j, you have to have a 2j added to the t squared over 2, because that would give you a 0. So you need to have a 2j, so that would be fine. This would have to be a coefficient of 1, which we determined before. But this one doesn't have an additional component because that needs to be 0. Okay? So just leave it t squared. If that was a t squared plus 7, then the k component of the constant would have to be minus 7, so that would add to 0 at t equals 0. Yeah, so. All right, any questions on that? That finishes just the velocity and acceleration. Now let's apply those to two-dimensional motion, which we call projectile motion, okay? And both of you had physics yet? I know you have, right?
I'm taking it now.
Taking it now. Have you had physics yet, or do you need to? Okay, so you haven't taken it yet, or you are? Oh, physics 1. So you're probably familiar somewhat with projectile motion. Motion, that's what physics 1 covers. Motion, velocities, accelerations, Newton's laws of force law, all those type of things. Well, this is part of that, projectile motion. You now have the machinery to divide the parametric equations for the path of a projectile, wherever it's heading. Assume that gravity is the only force acting on a projectile after it is launched. Now, that's not a very safe assumption in the real world, because you almost always have friction drag from air resistance, okay? But as long as that's sort of minimized, you can treat this as such. Okay. Muhammad is here. Okay. And by the way, I sort of hate to put this while I'm doing, but I won't call any names. Yesterday, we had to do it by today. I did it yesterday. Do a attendance verification. And of course, all of you have been attending fairly nicely, okay, without too much problem. But when I went to do so, a couple of you weren't even listed on the roll. And I assume that means there must be some issue with payment or something. So if you think everything's covered, it may not be. So go down and check with them at, I don't know, records office, financial services, somewhere, and see, because your names weren't on the roll. But you've been coming, so it wasn't an issue for attendance verification. It's just I was surprised you weren't here, and I knew you had been here. So please check that out. Okay. So, sorry. So, you now have the machinery to do. Assume gravity is the only force acting on the projectile after it's launched. As long as the speed is not too great, that's not a bad assumption, okay? But once you get a very fast speed, the velocity is, the larger the speed or velocity, the more air resistance, okay? So, motion occurs in a vertical plane, which can be represented by the XY coordinate system, okay? As the origin, with the origin as a point on the Earth's surface, okay? That means anywhere out here on X, that's also on the Earth's surface, okay? But you don't have to launch a projectile from the Earth's surface. You could do it from some initial height. For instance, that could be a plane dropping a bomb or launching a missile or something like that. A missile usually means you have some additional acceleration. So let's just say a bomb or something like that. And so it would have an initial height other than 0. It could be that you're on the upper deck of a ship, and so you're well above the water line. So that would be an initial height. It could be you're on top of a hill, firing down into a valley, and the valley is your x equals 0, or y is equal to 0. So any of those. But we're going to fire that projectile, so this wouldn't be the plane dropping a bomb. We're going to launch the projectile somewhere, but as soon as it leaves the source, there's no more force on it. Okay, that's just going to be. So this could be a weapon whose barrel is pointed upwards, whether it's a rifle or a cannon or whatever. That's the initial velocity. V sub 0 is this v at time t equals 0. Your r of 0 is your initial height. Okay. Your v of 0 is this. Your acceleration is always gravity. Remember, we said it's the only force acting on the projectile, so therefore it's the only acceleration acting on the projectile is gravity downward. That's acting on it here and here and here and here and here. Everywhere it is, gravity is pulling it downward until it hits the ground again, and then it stops. Okay? So that's your picture here. A is a constant acceleration, always downward. V is a variable velocity. It starts off at a fixed velocity, but that velocity is going to change as you go because gravity is pulling it downward, so it's going to bend it downward until right here. This is not. They make it seem like that's almost the top of this parabola. It's not quite. How I know that is the tangent is going off like this. If you moved a little further on here, then you would have a horizontal tangent line. Okay? And then the velocity vector is downward after that. Okay? But acceleration is always straight down. Here, 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 everywhere in between. Doesn't change. Constant magnitude, constant direction. All right. So that's your projectile motion picture there. For a projectile of mass m, the force due to gravity is minus mgj. Now, what in the world do we mean by g? If you haven't had physics, it might be new to you, but if you have, you should recognize that as the acceleration due to gravity. Acceleration due to gravity in the U.S. customary system is 32 feet per second squared, and the SI system 9.8 meters per second squared. Now, they like to say meters per second, feet per second, which is fine. It's perfectly correct, okay? In fact, it may actually be a little more correct than per second squared, because what in the world is a square second anyway? I don't know. It doesn't have dimensions, okay? But it's per second, which we shortcut it to say per second squared. By Newton's second law of motion, that same force produces the acceleration, A is equal to A of t, and satisfies the equation F is equal to ma. Okay? Consequently, the acceleration of the projectile is given by ma, that's this thing here, is equal to mg minus mgj. Now, why is the minus sign there? Because you assume that y is positive upward and acceleration is always negative. And g is not a dimension quantity, a sign quantity, it's just a number, so you have to put the minus sign in front of it. So if you divide both sides by m, you have acceleration is equal to g minus gj. In other words, the acceleration vector, just like we said, pointing downward, fixed amount, g, which is either constant 32 feet per second squared or 9.8 meters per second squared, but pointed downward in the negative j direction. That's your acceleration of the projectile at every point. Is that the only force acting on it? Then that's the only acceleration on it. All right. So here's example 5. A projectile of mass m is launched from an initial position r0 with an initial velocity v0. Find its position vector as a function of time. Okay? Notice they don't give you any more than any numbers in here. There's just vectors, r0 and v0. So find the position vector, which is r of t, as a function of time. So, what did they just tell us about the acceleration? Say that again, minus g, j, is that what you said? Yeah. Acceleration is minus gj. That's the net force acting on it is the acceleration due to gravity, so that is the only acceleration acting on it. Okay? Now, we also know that this is, I should have left more room. Again, I wasn't thinking ahead. Your A is equal to dv dt. Okay? So again, multiply both sides by dt. Integrate both sides. The g is a constant. And you have v is equal to minus, what would that be? Minus g t j. Perfect. Okay? Now, plus some constant c. And that's a vector, by the way. Okay? Some constant vector. But we know that the initial velocity, v0, so when t is equal to 0, this c is your v0. Okay? Now they like to use 0 there. It's fine. But when I do it, I like to say VO, meaning original velocity. V0 just sort of indicates that when t is equal to 0, I guess, but that's, I would say VO, but that's a 0. That's not an O. O's are more rounded, zeros are more elongated. That's a 0. So that would imply when t is equal to 0, which in this case, that's exactly what it is. So there's your velocity at any time is minus g t j plus v0. Okay. My head's clogging up on me again, so I'm sort of a pain in the neck. Okay? Now, this v of t is also dr of t dt. Okay? So that's equal to minus g t j plus v naught. Okay? Okay, initial velocity. And if we sort of like multiplying through both sides by dt, and now integrating that, you get r of t integral is what? Oh, integrate this and integrate this. What would that give you? Again, pull the minus g out. What's the antiderivative of t dt? T squared over 2. Okay? J plus, now, here's where things get a little more complicated. The V0, we don't know anything about it. We don't know what directions it are. If it's I and J, just I, just J, I, J, and K. I mean, we don't know anything about it, so it's sort of hard to integrate, okay, except just calling it V0T, whatever it is. But then you're going to find some other constant C. Okay? Now, when t is equal to 0, this would be 0, this would be 0, so the C, and that's the vector C, has got to be your R0. When t is equal to 0, that's its initial position. This is your R of 0. I'm going to write it that way. So what does that give us as our position vector as a function of time? R of t is equal to minus gt squared over 2 j plus whatever that initial velocity was as a vector times t plus whatever your initial displacements are as a function. Okay, at t equals 0. Sorry, there's nothing more written there. Yeah. Okay. I think that pretty much does it. Yeah. So your R of t, your R of t is minus 1/2 gt squared over, gt, 1/2 gt, minus 1/2 gt squared j plus your tv, I don't know why they put the vector second, and then the R0. Okay, that's it. So you can leave that part out. Plus R0. Okay. And that's in the gray box at the bottom of the page. Okay. They are introducing something new at the bottom there. In many projectile problems, the constants R0 and V0 are not given explicitly. Often you're only given the initial height, which would produce the R vector, and the initial speed, V0, and the angle theta at which the projectile is launched. And from the given height, you can deduce that R0, the initial position, is whatever that h is, j. If all you're going is up, okay, not going out at an angle or digging a ditch or something, just going up, straight up, then that would be h times j, okay? Because the speed gives the magnitude of the initial velocity, it follows that your v0 speed gives the magnitude of the initial velocity, so v0 is the absolute the magnitude of v0. So that just seems intuitively obvious. I don't know why they're writing it down. And you can write the initial velocity as xi plus yj, if you knew what those were, but that's your initial velocity, the magnitude of that, times the cosine of the angle. That gives you your x component, and the sine theta gives you your y component. So it's the same type thing that we've seen, you'll see in physics a lot, is writing those displacements in terms of sines and cosines. Cosine being x and y being sign. Okay, let's see how they did the problem. I don't know if they go into that much detail, but let's take a look at it. Begin with the acceleration vector, which we saw before was minus gt, gj, okay? Integrate it twice, and first time you get the velocity vector, and they put a C1 here, and they found out the C1 basically has to be your V0. When you integrate the second time, you get negative 1/2 gt squared j plus C1t plus C2. Why they haul those around, I don't know. And you can use your initial conditions, V0 is 0, V at 0 is equal to V0, and R at 0 is R0, and solve for the constant vectors C1 and C2, which we did as we went. That produces C1 being V0 and C2 being R0. Therefore, the position vector is minus 1/2 gt squared j plus TV plus R0. Okay, just like we found. What's the question? Okay. And it says here, many projectile problems, the constant vectors R0 and V0 are not given explicitly. Okay? I think I just read that, yeah. So this is all the same thing we just were saying. I wish I'd have flipped ahead. I didn't know they were going to print this. If this is your initial velocity, okay, your initial displacement is just up here, and that's h times j, okay? H times j, y unit vector is j, okay? Your initial velocity is like this. That's your xi plus yj, where your x is if you know that initial velocity, not by components, but just by the initial velocity, and you know the angle, then the x component is V0 times the cosine of theta, the y component is V0 times sine of theta. Okay. That's how you get those values. What I was calling V0 was in other places, right here, this V0. Okay. They put it in vector form, which is that little V0. Okay. Now, from the given height, you can deduce the R0. We already said that. Speed gives the magnitude of initial velocity, blah, blah. So, yeah, we've done all that, yeah. And this is what we got. The initial velocity vector is V0, meaning the speed that was given, cosine of the angle that you had to have given or measure it somehow, I plus V0 sine theta j. Now, I really don't like this notation because it looks like the theta and I are connected somehow, and they're not, okay? If I were writing this, I would either put the cosine theta in parentheses and the sine theta in parentheses, and maybe a space or something out there between the I and the j, you know, so that gives it a little bit of room there. Or what you could do, and this math books don't usually like this, is put the I with the V0 and then cosine theta after it, so you don't confuse the I's with the thetas. Okay, but that's a little, math books have trouble doing that. All right, now, so we've got those done. Those are basically the bottom of page 840. So the position vector, here we're going back to this again, and this still is the bottom of 840. The position vector can be written in the form of R of t. This is from your acceleration, always pointing downward, minus 1/2 gt squared in the j direction, plus t times v0. Now this is the vector v at time t equals 0, for your velocity vector at time t equals 0, plus r0. It's exactly what we had before, but then we take this and plug in this V0 is, see, this is vector V0, this is speed 0, meaning italicized V0, which is the magnitude of that, times cosine theta I plus the magnitude of that times cosine theta j, and then the HK, that was your displacement vector. Okay? So, to put all these together, here's your I component. That's the only component in the horizontal direction. Okay? That's constant throughout the problem. Okay? And then your H is your initial velocity plus your component of your velocity vertically, which is going to increase the H, but your component from the acceleration is going to be decreasing it. So you have competing things here, whatever you started, plus wherever your initial velocity started you heading, but then minus wherever the acceleration was pulling you in the negative direction. So that's all your J components there. And it kind of makes sense physically if you think about it in those ways. Okay. Finally, we get to the top of 841. I thought it would never come. Position vectors for a projectile, neglecting air resistance. Now, remember I said that at the very beginning. The path of a projectile launched from an initial height h with initial speed v0 at some angle of elevation theta that's described by this vector function. R of t is equal to that v0 cosine theta, that's the horizontal component of that velocity, times t in the I direction. And then in the j direction, you've got your initial position, just h, just a constant, plus your v0 cosine theta t, that's your, how much that's changing due to your initial velocity in the j direction only. And then the acceleration that's pulling you downward, the acceleration due to gravity is minus 1/2 gt squared in the j direction, where g is the acceleration due to gravity, depending on what unit you're in. 32 feet per second squared in the U.S. customary system, or 9.8 meters per second squared in the SI system international. Okay. Here's example 6. Describing the path of a baseball. A baseball is hit 3 feet above the ground. That sort of makes sense. If you swing a baseball, usually you make good contact with it, it's going to be right about waist level. You know, that's going to be good. So 3 feet above the ground is where he's hitting from. Okay? Maybe he's playing T-ball. I doubt it. Okay. At a level of, at 100 feet per second, at an angle of 45 degrees. Now, this is supposed to be the horizontal here, okay? 45 degrees. It doesn't look very horizontal, but that's what they're intending, okay? 45 degrees with respect to the ground is shown in this figure. Find the maximum height reached by the baseball, okay? Now, I think they've given us everything we need for that. So, what is our the basic equation for projectile motion that we were just given? R of t is equal to, you remember it? Second? 0. Oh, v sub 0. Yeah. Okay. All right. Okay. V sub 0 cosine theta ti, you got it. Okay. Plus h, that's your initial height, plus v0 sine theta, I like to put in parentheses t, minus Remember? 1/2 GT squared. And then all this is times J. We're dealing with only two-dimensional motion here, no three-dimensional motion, even though, yeah, it's out in space, but the path of the baseball is two-dimensional. Where the horizontal is how far it's going on X, vertical is how far on Y. Okay. Now it says find the maximum height reached by the baseball. What is the height reached by the baseball? It's the J direction, right? How do we find the maximum? Last class, someone popped it right up because that's all they did before. You take a derivative, okay? And you find out where that derivative is 0, because that's going to represent the maximum height. This is a quadratic equation. Maximum height is going to be where that derivative is 0, okay? So let's do that. Let's deal only with the J direction, okay? That's going to be the height, is the J. So let's call that Y. Why not? Y is equal to H plus V0 sine theta T minus 1/2 G. Yes. Oh boy. Now, I don't know if that's the bulb or that's one thing the gal said. She said this might happen, and I think she was absolutely right. I've just yeah, I'm going to try that one. That was my next move, but this is not. See, it did it on my other one, and we determined, or we thought we determined, the cord was bad. She said, no, I'm afraid your computer's bad too. And it may be. I'm still hoping it's the box over here that's bad, but I'm not convinced that's going to be the case. That's why I brought 2 of them in here, in case one of them didn't work. It still will record, it just won't show on the board. So that means it's really a pain in the neck. It's not exactly what it's supposed to mean, but that's what it does mean. Now this does not look good at all. This has been bent up. This one's no good. Yeah. I don't know who did that, but it wasn't me. I can't even get this to plug in. The housing is bent. Now, what I may try, I will try, is see if I can force it in here. Maybe this is that's not going to work. I don't know if y'all are familiar with these things, but you see this part of the thing here. It's not going to work. Now this then makes me suspect, like she said, there's something wrong with my computer too. And she suggested that since it landed here and broke off some pieces here, this whole mechanism in here probably has been damaged. So means I've got to return these to the room I stole them from, borrowed them from. I had permission. Now this is discouraging. It has not come back. This is what happened in my last class, and I had to teach the rest of it from, and I don't know why it changed. I didn't do anything that I know of.
The color didn't change until you started playing with the screen.
Huh?
Yeah, I said the color didn't change until you started playing with the screen.
Yeah, and what I did, I'm sure that it bumped into something back here, as I did that. And now I've lost it completely. Oh. Okay, let's see if we can keep it going this time. All right. 1/2 GT squared. Okay, that's your y component. Okay, and let's take y prime. And what would that be? The h goes away. I mean, that's a constant, so that doesn't contribute. And this becomes v0 sine theta without the t minus gt, right? Now, the question is, where is that equal to 0, right? No, okay. We're not taking the derivative with respect to theta. Theta is fixed. It's 45 degrees. I should have probably already put that in there, so we don't even suspect it. See, the angle there is 45 degrees. That's not changing. There's no change of theta, so there's no derivative with respect to theta. The V0 is 100 feet per second, okay? So I probably should have put that in there, and the G is 32 feet per second squared, since everything else is in feet per second squared. So I should have already done it. I was just lazy. Okay, so this is 100 feet per second times the sine of 45 degrees, which is the square root of 2 over 2, right? Y'all remember that, don't you? Say yes, okay. Minus, huh? Oh yeah, you're right. No, okay. Now, number one, no. Okay. I just answered that one. Theta is fixed here. We're not taking the derivative with respect to theta. It's only with respect to time. Okay? That's the only, this is your variable here. This is a constant. Theta is 45 degrees. V0 sine theta, that is fixed. V0 is 100, sine theta is 45. That is fixed. That's the, I could have said sine theta 0, your initial, thing. That is, I should have gone on and just written that in as this the very beginning, and you just see it's a constant. And this is fixed too, as 32t. 32, I'm going to leave off the units for now. 32 times t. And we want to set this equal 0. What I'm going to do is take half of 100 and make it 50. So this will be, set this equal to 0. And what we have then is 32t is equal to 50 root 2. Okay? Divide both sides by 32. And you have t is equal to whatever that is, 25 root 2 over 16. Whatever that is, plug it in and see. 25 root 2 over 16. And that would be 2.21 seconds, the book says. That's when, okay, find the maximum height, that's when the maximum height was achieved. Well, we still don't know what the maximum height was, so we take that number and we plug this, and this will be seconds, by the way. We plug that number into this y position. And the h, by the way, is 3, so the y max, okay, is going to be 3 plus, and this was your 50 root 2. That's your V0 times sine theta. And then we're going to multiply that by your 25 root 2 over 16. That's your t. Minus 1/2 g. Let's just make that 4.9. Okay. No, I'm sorry. I'm doing SI units. Sorry about that. Make that 16 times t squared. That's 25 over 16 squared times 2, because I'm squaring my root 2 separately. Okay? Now, that's a weird way to write it, but I hope that's all right. Notice what we can do here, if I could read my writing. Here, this root 2 and that root 2 multiply to be 2. And this is a 16 here. I'm going to leave that alone. Make it 3. Oh, let's just divide that 2 into 16 and make it 8. We'll divide 2 into that and make it 25. I can't get my pen to work. And a 4 down here. Okay. So it's 3 plus 25 squared over 4. That's 625, I believe. You can check me on that. Minus, and one of the 16s goes out, but you still have a 25 squared. Over 8. Okay. Because the 2 will go into the other 16 8 times. Okay. Well, the difference between these two is 25 squared over 8. Okay. Plus 3. So I think this is 625 divided by 8. If someone's got a calculator, second? 156. Second? Okay. Plus 3. Did you add 3 to it already?
Yes.
Okay. So that should give you your height. What did you say it was?
It's 156.
156? Okay. Wait. No. Wait a minute.
Is it 3 plus 25 squared over 8 or over 4?
Over 8, I believe.
Because over there we had over 4.
Okay, yeah. But then I subtracted that from here, and that gave me over 8. Yeah. Okay. So 625 over 8, and add 3 to it.
78.
Huh?
78.
78 plus 3 is 81. Did you already add the 3 to it?
So it's 3.
Okay. This thing right here is 625 divided by 8, and then add 3 to that number.
6.
Okay, and that gave you maximum of 81 feet. So that's the maximum that ball height the ball had over the ground. Is that right? Yay or nay?
Yes. 80.
Okay, 81 feet. Okay? Now, the next question is, so find the maximum height reached by the baseball. We got it. Will it clear a 10-foot fence located 300 feet from home plate? Okay, you said no. Okay, and here's how you do that. Okay, you know that this right here has got to be 300 feet, right? That's how far that is. Okay, so if that's 300 feet, then divide, and by the way, V0 cosine theta is the same as V0 sine theta because 45 degrees are the same. So that's going to be, what was that? 50, oh, what was it? 25 root, no, where was it? I had it. I'm just all over the place here. There it is. No. V0 is 100, and yeah, so it's 50 times root 2. That's what it was, 50 times root 2. Okay? So 50 root 2 t is equal to 300. Divide both sides by 50 root 2. Okay? Well, 50 will go into 300 6 times, won't it? Yeah. Okay? So it's 6 divided by root 2. So that's what time it'll take to reach the fence. T is equal to 6 over root 2. And you figure what that is. That'll be seconds. All right? .24 seconds. Okay? So the question now is 3 plus, that was 50 root 2, right? Yeah. Times 4.24 minus 16 times 4.24 squared. Okay? Figure out what that is. Is that greater than 10 or less than 10? You said you didn't think it would. Let's see what it will do. If you plug 3 times 50 times root 2 times 4.24, it's 53 plus that, minus 16 times 4.24 squared. See what you get. That's going to be greater than 64. This is going to be, probably pretty close. What you get?
Say minus 4.24.
4.24 is what you told me the time was. So that's what you're doing. You're plugging in the time, 4.24, in both of these. If you got from here, plug that time in here and see what you get.
So it's supposed to be less than 10?
Second?
You said it's supposed to be less than 10?
No, I'm asking you, is it 10, greater than 10, less than 10?
15.
15, all right, you cleared it by 5 feet, right? Yeah, so I don't even think a good jumper out there could do 15 feet up, could he? Well, maybe Terrell could. Yeah, probably, if you use the fence to push off on. Yeah, of course, okay. So yes, it did get to 15 feet. It clears it for a home run. Unless that was a foul ball. No, okay. Never mind. We won't go there. That finished 12.3. Homework exercises here. Do any of the odds 3 through 9. All of those are at calcchat.com. 3 is at calcview.com. Do any of the odds 11 through 19. All of those are at CalcChat. 15 is at CalcView. Do any of the odds 21 to 25. They're all at CalcChat. 21's at CalcView. do any of the odds 27 to 39, okay? They're all at Calc Chat. None of those are at Calc View. Then do 41. It's at Calc Chat, but not at Calc View. Then do 43. 43, it's a Calc Chat, not a Calc View. Then do 45, it's a Calc Chat, but not a Calc View. Then try to do 47 or 49, or both if you choose. They're at Calc Chat. And then 51 is a Calc, no, yeah, 51 is a Calc Chat. You can look at 53 and 55 if you'd like. There's nothing really to calculate there. It's just sort of thinking through it. 57 is a reasonable problem, probably a little on the difficult side. You can give that a shot. And if you want to do a proof, that's 59. True, false, two of those, 61 and 63, all those should be at Calc Chat. If you can't find them at Calc Chat, don't worry with them. Okay, let's see. Oh, let's see how they work the problem. You're given h is equal to 3, v0 is equal to 100, theta is equal to 45. See, those are fixed numbers. They're not variables. They're fixed, okay? So what they do is, I don't know why this makes no sense to me, but it's okay. Using theorem 12.3 with g equal 32 feet per second, and that produces 100 times the cosine. Why do they put pi for us? Why don't they put 45 degrees? I mean, it's the same thing, and it was given that way. Why change it to radians? I don't know, okay? It's sort of like, we're doing calculus now, you can't use degrees anymore, okay? And that would be your ti. That is your horizontal component of your velocity, and however long you go, that's how far it goes. This is your vertical component, 3 plus 100 sine of pi force rather than 45, t minus 16t squared. That's the 1/2 of 32, okay? And that's in the j direction. All right. Now, that is 50 root 2 ti, exactly what we got, plus 3 plus 50 root 2t minus 16t squared j, exactly like we got. And that came up, the velocity vector is then this, which is 50 root 2i plus 50 root 2 plus 32 tj. And the maximum height occurs when your y component, which is the j component there, is at a max. So you take the derivative of that, and that gives you t is equal to, boy, they sure didn't show it well, did they? Set that equal to 0, okay? So set this equal to 0, move the 32 t on one side of this, so 50 root 2 divided by 32 would be 25 root 2 over 16. Exactly like we got, okay? Now, that's approximately 2.21 seconds, okay? Now, maximum height is reached by the ball that came from your first derivative of that. Go back and plug it into what your maximum height is, the y component is, plug that in, and it's sort of a pain in the neck to look at, but it's really not that awfully bad, because the root 2 times root 2 is just going to be 2, and 2 will go into the 16 here 8 times, and then you can do another 2 from here into that, and that gives you 4 times, so you get 25 squared over 16. No, over, what did I say? 4, okay? 25 squared over 4 here, minus, and, okay, one of these 16s goes out, so that's what that one. The root 2 squared is 2, so the 2 goes into the 16 8 times, and it'd be 25 squared over 8. This is 25 squared over 4. The difference in those two is 25 squared over 8. Add that to the 3. I'm sure that's not how they did it, but that's how we did it. And they just came up with 649 over 8, which is kind of cheating, I think, but, you know, it's okay. And then when they did that, that's about 81 feet. That's at about 2.21 seconds. That would be your height, 81 feet. So that's the maximum height the ball achieves. I don't think even Terrell could reach that one, so he can't jump up there at the maximum height and get it. He'd have to wait till it came down. So the ball is 300 feet from where it was hit. When does that occur? When the exit T is 300. Well, exit T is 50 root 2T. Set that equal to 300, divide by 50 root 2, and that gives you, goodness, how, yeah. All right. How did they get that? Well, 50 will go into 300 6 times, and divide 6 by root 2, well, that's the same as 6 root 2 over 2, and the 2 goes to 6, 3, so it's 3 root 2. And that's 4.24 seconds, which is exactly what you got. Now, I want you to notice something here. That's not quite the same as, well, no, never mind. It has really nothing to do with it. Well, it sort of does. Let's go back. Your maximum height was reached at 2.21 seconds, okay? You're reaching the fence in less than half that time, right? Because half the time, twice that time would have been 4.42 seconds, and you've reached it in 4.24. So you're less than half the time, so there's a pretty good chance that it might go over the fence. So what you do is take that time and plug it into, why didn't they use 4.24? But they went back and plugged in 3 root 2. So 3 plus 50 root 2, that was your V naught sine theta. Okay. And this is the time, and then that would be minus 16 times the time squared. Well, again, the root 2's multiplied would be 4. 4 times 50 would be 200, times 3 would be 600. So here you would have 9 times 4 is 36, times 16. So you just have to do the multiplication, see what you get. And sure enough, it comes up 303 minus 288, which is 15 feet. The height, when you reach that 4.24 seconds, it clears the 10-foot fix for a home run, but not too much chance of anyone being able to snag that. All right, that was the end of the section. I've already made the assignment, so what I need to do is discard that. And how are we? Ooh, goodness, did we just go over? We did. Yeah, well, guess what? No extra charge, okay? Because my projector went out. So we'll start next time at 12:04, okay? Yes, sir.
I have registered for this.
What's that?
For me, I check on the class I have this. I'm supposed to register. So this is my schedule. So this semester I already registered for. So I went to the Blackboard. I don't have your class on my Blackboard. So who should I see about?
You're not listed on Blackboard.
No, on Blackboard I don't have your class on there.
Do you have the other 3?
Yes, I have the other 3 on there, but except your class.
Okay.
So if I go to Blackboard,
That sounds like a Blackboard problem, so let's see if we can track that down. Were you in the same boat, or did you think everything was covered, or?
Everything should be covered because I have to pay cash, so I've already paid. So
Yeah.
it shouldn't be a money problem.
Okay.
So I don't know.
When, do you remember when it was you paid? Long time back? Okay.
because on my back, for me on Student Suite, it says I'm registered, everything is clear. But I go to Blackboard, this class is not added on there. So I have my other classes, but your class.
I don't know. Huh?
It's on there for me.
Okay, you're on Blackboard. Okay, so that's not the issue, I guess, but I don't know what the issue is. Let's see if we can figure it out. go somewhere, find out what the problem is. Okay. So you have any receipts on you today? You probably don't. You don't. Does that indicate everything's okay? Can you tell
I
me?
mean, it's